Hello, my name's Thanom and I'm from UNSW. Today I'm working through some of the Math 1011 calculus questions from the section on integration and areas. In question 2a, we're given a table of values here showing the maximum daily temperatures recorded during 1 February in Sydney. I've graphed those values over here. So I've got the day in February along the horizontal axis and the temperature in degrees Celsius here. We're only given these points, so every 4 days, what those maximum temperatures are. I've just drawn a dashed line in here just to indicate that we don't really know what's happening in between, right? The graph of the function of the maximum temperature could be doing anything in between those values there. So I've just drawn a dashed line. Now what we're asked to do is to use Riemann's sums to estimate the average maximum temperature during February that year. So we're trying to estimate the average of this temperature function. So this is a function here, this dashed line if you like, and I want the average value of that function. If I want the average value of a function, I need the area under the graph, and that's what I will be using Riemann's sums for, to estimate the area under that graph. Okay, so we're asked to do it twice. First, to use the left-hand endpoints for the Riemann's sums, and second, to use the right-hand endpoints. Okay, so we'll estimate the area, and then we'll find the average value of that function, or at least an estimate of the average value of that function. Okay, so the idea is, if I'm using the left-hand endpoints, I'm using Riemann's sums, so I'm estimating the area under this dashed line, say, using rectangles. So in this strip here, we've got 7 subintervals. Here they are, every 4 days in February. And I'm going to estimate the area by drawing horizontal lines at each of those left endpoints there. Okay, so this area, etc. Okay, so for each of the 7 subintervals, I take the leftmost point and draw a rectangle, and I use that rectangle as an estimate for the area under my function. So my 7 subintervals across here, and the leftmost endpoints are the tops of the rectangles that I will use for the Riemann's sum. Okay, so the area, using those leftmost endpoints, the area is going to be the area of each of these rectangles. The area of a rectangle is the base times the height. So the base of each of these rectangles is 4. So the area is going to be 4 times, this height here is 29. That 1st of February temperature is 29. So this area is going to be approximately 4 times 29 for that first rectangle, 4 times 32 for the second rectangle, 4 times 36, I might just put these in brackets so you can see each of the 7 rectangles, 4 times 28 for the 4th rectangle, 4 times 30 for the 5th rectangle, 4 times 25 for the 6th rectangle, and 4 times 22 for the 7th rectangle. So I'm estimating the area under this temperature function using the leftmost endpoints as the heights of my rectangles in the Riemann's sum. Okay, so this calculation turns out to be 808. So that's an estimate of the area under the curve. So if I want the average value of a function using that estimate, so the average value of my function over the interval from a to b is given by 1 over b minus a times the area under my graph. So therefore, the average value of the function, or the average maximum temperature, because that's what my function is about, using this particular estimate is going to be 1 divided by, well, 29 minus 1 multiplied by the area under that graph, which was 808 approximately in that case. So I'll write approximately, and that turns out to be 28 6/7 degrees Celsius. Okay, so if I use the leftmost points, an estimate for the average maximum temperature during February is 28 6/7 of a degree. Now, for the second estimate, I'll just change to green here. So if I want to use the right-hand endpoints, then I've still got my 7 subintervals here, but for this first subinterval, I use this rightmost endpoint, and I calculate the area. I estimate the area as the area of this rectangle here. So in the second strip, the rightmost endpoint is here. In the third strip, the rightmost endpoint is here. In the fourth strip, the rightmost endpoint, the rightmost endpoint, the rightmost endpoint, and the rightmost endpoint. Okay, so as our second estimate, we'll be using the areas under these green rectangles, and that will be my Riemman sum, estimating the area under that graph. So using that, our area, our first rectangle will have a base of 4, but this time a height of that rightmost endpoint, which is 32. So it's going to be 4 times 32 for the first rectangle. The second rectangle is going to be 4 times 36. The third rectangle is going to be 4 times 28. And then 4 times 30. And then 4 times 25. 4 times 22. And the very last rectangle is going to be 4 times 27. So the heights of my rectangle are now shifted to the right endpoints, which are the 32, 36, 28, 30, 25, 22, and 27. When I add all these up, I get the number 800. So that's an estimate of the area under our temperature graph. And so if I use that as my estimate, the average maximum temperature is going to be approximately 1 on 29 minus 1 times that 800, and that gets me 28 4/7 of a degree. Okay, so in this question, what we were doing is we were using Riemman sums with the subintervals they gave us to estimate the area under the graph. Depending on whether we chose the left endpoints or the right endpoints, we got slightly different estimates there. So as an estimate of the area just under, say, that dashed line. And then once we had the area under the graph, we could find the average value of the function using this formula here, which is essentially, I guess I could draw the line on. So this dashed line here, this is saying the average value is 28 6/7 or 28 4/7. So if I could draw a line across at 28 4/7, so maybe somewhere here. So that's saying on average, my function is at this level, right? So if I spread all that area out between the 1 and the 29, this would be the average height of that function there. So 28 4/7 is just slightly under that.